Hello and welcome to Quantum Mechanics Made Easy, the beginner problem playlist. My name is Dr. Jacob Hudis. Today's lesson is titled A Complete Guide to the Hydrogen Wave Functions and Atomic Orbitals for Every Element on the Periodic Table. Woohoo! Yeah! In the beginner problem playlist, I will solve quantum mechanics problems that don't involve pages of algebra. And here's an outline. To begin, I will set up the Schrödinger equation for the hydrogen atom. Next, I will discuss the wave function boundary conditions. I will present solutions to the differential equations without lengthy steps of solving the partial differential equations. All necessary math and concepts will be included to provide the full quantum mechanical picture. I just won't go through and solve the differential equations, at least not in this playlist. This method prevents students from getting lost in complex calculation. It emphasizes understanding of the overarching concepts. This is the big picture first approach. It focuses on understanding the solution and their meaning rather than just solving equations. Near the end of this presentation, I will present an example problem to help aid in the understanding of atomic orbitals. I will finish the presentation by showing some of the best visual plots of the hydrogen wave function available on the internet. There will be a part 2 where I focus solely on these visualizations. AI voiceovers will be used on occasion. Please leave your thoughts and comments and let me know what you think of the AI voiceovers.
In this presentation, and more extensively in Part 2, I will use wave function visualizations from Quantum Physics Online, created by Professor Manuel Joffre. With his permission, I am sharing these exceptional visualizations, which are among the best available. You can explore them for free at the link provided in the description of this video.
Hi, and now's the moment that you've been waiting for and thinking about and dreaming about for many, many years. I am about to discuss the hydrogen atom in terms of quantum mechanics. The hydrogen atom consists of a proton at the nucleus and an electron which orbits the proton. Now, the electron does not orbit the proton the way that you'd think of a planet orbiting a sun. The electron is spread out into a wave function, and so this picture is not correct quantum mechanically. However, the electron does have a negative charge, and the proton does have a positive charge, and therefore there is a potential energy of this configuration. The potential energy of the electron at distance r from the proton is given by the well-known and established equation from classical electromagnetism, and this is U of r is equal to negative ke squared over r, and this is equal to negative ke squared over the square root of x squared plus y squared plus z squared in the Cartesian coordinate system, named after the French mathematician René Descartes. Now we want to use quantum mechanics to solve the hydrogen atom. Step 1 in almost any quantum mechanics problem, and certainly in this very important one, which is learning about atoms, is to write down the Schrödinger equation.
Too easy.
We all know the Schrödinger equation. We love it. We have it tattooed all over our bodies. We have it painted on our walls. So this is the Schrödinger equation. Of course, you know that. Step 2 is to replace the potential energy with the potential energy associated with the problem. In this particular case, the problem that we're dealing with is the hydrogen atom, and so the U is going to get replaced with negative ke squared divided by the square root of x squared plus y squared plus z squared, and this is the Schrödinger equation for the hydrogen atom. Yo!
Terrific!
This is U of r, the potential energy associated with the hydrogen atom. And as you notice, the potential energy only depends on the radial distance r. There's no theta or phi dependence.
Why is this important? To use the technique of separation of variables to solve the Schrödinger equation, the potential must be separable. In Cartesian coordinates, the potential is not separable. However, in spherical coordinates, it becomes much simpler to solve the differential equation. By using spherical coordinates, we can simplify the complex problem of solving the Schrödinger equation for the hydrogen atom.
All right, to reiterate what I was just saying in my British accent, there are two very important coordinate systems that we use in physics. One of them is the Cartesian coordinate system, and another one is the spherical coordinate system. This point P can be represented by some location on the x-axis, some location on the y-axis, and some location on the z-axis. It can also be represented by some angle theta, some angle phi, and some distance r, or sometimes it's called rho, from the origin. The potential only depends on r, and you have some sort of symmetry in the radial direction. What you would want to do is use these spherical coordinates. This is the Schrödinger equation written in spherical coordinates.
Let's go.
Wow, isn't that beautiful? I've just presented this equation without a lengthy derivation, but it's simply math. This is just the same Schrödinger equation that we know and we love deeply, but this is written in spherical coordinates, and so this can be applied to problems with spherical symmetry like the atom. I think I have to move on because if I stare at this much longer, I'm going to have some sort of an episode.
Oh.
I don't want that. You may, I don't have time for that today. This is the Schrodinger equation for the hydrogen atom. All we've done is we've taken the potential energy and replaced it with the specific potential energy for the hydrogen atoms. This term here is negative k e squared over r. And then you replace mass with the reduced mass. This is a little bit beyond the scope of this lesson. The reason we do that is because classically, if this electron is rotating around the proton, it's not actually rotating around the center of the proton. They're both rotating around the common center of mass, and the center of mass is slightly off center. It's slightly away from the center of the proton. Ultimately, this is the equation that we need to solve in order to learn everything there is to know about atoms. And this equation has been solved, and this is one of the major breakthroughs in modern physics.
This is the Schrödinger wave equation, which describes these waves. For the hydrogen atom, the solutions to this equation are standing waves that correspond to electrons. The waves are the electrons. The hydrogen atom wave function solutions reveal a lot about the periodic table of elements. The solutions of this equation provide immense insight. Typically, classes spend 1 to 2 weeks solving this equation. However, instead of solving it in this playlist, I will present the solutions in the upcoming slides. Excuse me, I think I just fried my nano chip.
What should the boundary conditions on psi be? Well, one is psi has to be well behaved, and if we take the integral of psi squared over all space, it has to equal to 1. What that means is if we're looking for the particle, the electron in this case, the electron has to be somewhere, and that means that the wave function must be normalizable. Another thing is as r goes to infinity, the wave function must go to 0. The reason is because this is the wave function which represents the electron, and the electron is localized in a wave, in a standing wave pattern, around the protons, around the nucleus. So if you go very far away from the nucleus, the electron's not going to be there. That's physics intuition. That's kind of common sense. And then finally, the electron forms a wave. The electron is a wave. And what this means is that if you start at this location and you come back to this location, the value of the wave at that point has to be the same. And so psi of r theta phi must equal to psi of r theta and phi plus 2 pi. That just means if you make a full rotation, the wave has to come back on itself. With the boundary conditions on the previous slide and the Schrodinger equation for the hydrogen atom, we're able to solve the entire problem. Solving the differential equation is involved, but what I've done is I've written some of the solutions here, and I'm just presenting them to you. The full solution to the hydrogen atom is written on this page, where n, l, and m are the 3 quantum numbers. This is a 3-dimensional problem, which means that there's 3 quantum numbers. One thing that we learned from the solution is that the energy of the electrons when they're bound into the hydrogen atom are quantized. The formula for the energy is negative 13.6 divided by n squared, where n is the principal quantum number and n goes from 1 all the way up to infinity. So the lowest possible energy that the electron can have is negative 13.6 electron volts. If the electron moves into its next available energy level, n would equal to 2, and then you'd have negative 13.6 divided by 4 electron volts. The wave function corresponding to n equals 1, you have n equal 1, l equals 0, ml equals to 0. We're going to go through and analyze these on the next several slides, so right now I'm just presenting this information to you. These are the quantum numbers, and if I want to know the wave function would be the r component multiplied by the theta component multiplied by the phi component. If I were to multiply these 3 functions together, that would give me the wave function corresponding to the energy of negative 13.6 electron volts. If I want the wave function corresponding to negative 13.6 electron volts divided by 2 squared or divided by 4, that would mean I need the principal quantum number of 2. And in fact, there are 4 possible states which have a principal quantum number of 2. It looks like there's only 3 here, but if you see this is ml equals plus or minus 1, so there's actually 4. If I look at the state n equal to 2, L equals to 1, ML equal to 0, the wave function for that state would be given by this function of r multiplied by this function of theta multiplied by this function of phi, and in this case the function of phi is just a constant. And if I multiply these two together, that gives me the wave function of the hydrogen atom, and in fact that would give me the wave function corresponding to any atom on the periodic table for an electron having 2, 1, and 0 for the quantum number pairs. So this energy value, along with the corresponding wave functions, this tells us all about the atoms on the periodic table, and this is what we want to go and analyze on the next several slides. To recap, this is the Schrodinger equation written in spherical coordinates with the potential energy for the hydrogen atom. If we solve this Schrodinger equation, we get the solutions for all the possible energy orbitals and energy values that the electrons can be in for the hydrogen atom, as well as for any atom with the same potential, which is every atom on the periodic table. The solution depends on three quantum numbers, N, L, and M. Like any quantum mechanics problem, psi is going to be a function of locations in space, so it can be x, y, and z, or r, theta, and phi if we're using spherical coordinates. The energy solution is negative 13.6 over n squared. There are three quantum numbers. N is called the principal quantum number, L is called the orbital angular momentum quantum number, and ML is the magnetic quantum number, or the Z component of the orbital angular momentum. The boundary conditions put restrictions on the quantum number. N must be an integer. It starts from 1 and it can take on any integer value going to infinity. L goes from 0 to n minus 1, and ML goes from negative L to plus L. For example, if n is equal to 3, then the possible values of L are 0, 1, and 2, because 3 minus 1 is equal to 2. When L is equal to 0, ML must be 0. When L is equal to 1, ML can be minus 1, 0, or plus 1. And when L is equal to 2, ML can be minus 2, minus 1, 0, 1, or 2. This is the result of solving the differential equation, and this gives the entire solution for the hydrogen atom as well as other atoms on the periodic table. Are you in need of a great physics tutor? Dr. Hudis can help. Whether you're preparing for a high school test, AP test, or college exam, let me help you ace it. Are you an eager high school student aiming to get ahead and prepare for college-level physics? Or maybe you're a college student and you want to learn even more advanced physics? Dr. Hudis can help. Visit acephysics.org and schedule a lesson today. The next step is to go and analyze these solutions.
The wave function squared, multiplied by a small volume, gives the probability of finding the particle within that volume.
One of the fundamental rules, just a postulate that was learned, a discovery of science, is that psi squared dV tells the probability of finding the particle in a small volume element around the location r, theta, and phi. Imagine that we go to some location r, theta, and phi. There's a value of the wave function at that location. If we square it and then we multiply by a small volume element, that will tell us the probability to find the particle within that volume element. In spherical coordinates, dV is equal to r squared sine theta dr d theta d phi. Unfortunately, we need to deal with this confusion because it's easier to solve the Schrodinger equation in spherical coordinates, but it comes along with this confusing fact that the volume element is different for different values of r and theta. The volume element in spherical coordinates depends on r and theta for the same differentials dr, d theta, and d phi. For smaller r, the volume element is smaller. Similarly, for theta near 0 and pi, the volume element is also smaller. Closer in on the r direction, you're going to have a smaller volume element for the same differentials dr, d theta, d phi. And if you're closer to theta equals to 0 or theta equal to pi, again, the volume elements are smaller. The probability to find a particle at r, theta, and phi is equal to psi squared times the volume element, and the volume element is r squared sine theta dr, d theta, d phi. We know that psi squared is equal to RNL times YLM. RNL is the radial portion, and YLM are the spherical harmonics, and that's just the theta portion multiplied by the phi portion. We put both of those together in the spherical harmonics because those never change. What does change is the radial portion. We can write all of the R terms together and all of the theta and phi terms together, and that's going to make analyzing the problem easier. In Cartesian coordinates, it would have been much harder to solve the differential equation, but one thing that would have been easier is that the volume elements in Cartesian coordinates are uniform. It's a discovery of science, a law of physics you could say, that psi squared represents the probability per unit volume, or the probability density of finding a particle. Therefore, psi squared multiplied by dV, a small volume, tells you the probability of finding a particle in a given volume. In the particular problem that we're discussing, atoms on the periodic table, psi has a radial portion as well as an angular portion. So you can write psi squared as r squared multiplied by the spherical harmonics squared, and you can separate this out into a radial portion as well as an angular portion. By separating the problem into radial and angular probability distributions, we can more easily visualize and analyze the solution. While this method aids in our understanding of the solution, it does not introduce any new fundamental physics. It's simply a tool to help visualize and understand the wave function. This portion turns into the radial probability distribution. The maximum values that we could integrate over would be from r equal to 0 to r equals infinity. But we could choose a smaller range, and if we integrate from r1 to r2 of r squared times little r squared dr, this represents the probability of finding the particle between r1 and r2 from the center, where the center is the nucleus. The probability in the phi direction is constant, and so we can integrate it out. For any one of these solutions, the phi portion is e to the im phi, and when you square that, you get a constant. None of these solutions depend on phi. The probability in the phi direction is always the same. P of theta is equal to 2 pi times the integral from theta 1 to theta 2 of the theta portion of the wave function squared times sine of theta d theta, and this represents the probability of finding the particle between theta 1 and theta 2 for all values of r and phi. On this slide, I've written down 3 wave functions. These are entire and complete wave functions, solutions to the Schrodinger equation. All of these have L equals 0. I chose this specifically because these don't have theta or phi dependence, and they're a little bit easier to look at first. These are the functional forms of the wave functions, and none of them depend on theta or phi, as you can see from looking. The probability density is plotted on this function, and so for psi 100 squared times r squared, you would mainly find the particle in this location. You can see that the wave function drops off to 0, and you wouldn't really find the particle farther out than that. Psi 200 squared, this is a particle which is farther out from the nucleus. It has less energy. It has negative 13.6 divided by 4 electron volts of energy. And for this wave function, you would find the particle at this location some amount of the time. You'd mainly find the particle along this location, and then the wave function drops off to 0 again. And for psi 300, this is the form of the wave function. In this case, there'd be a small probability to find the particle here, a bigger probability to find it here, and a larger probability to find it within this region. This three-dimensional plot might help you visualize it even a little bit better, and as you notice, there's no variation in the theta or phi directions for these particular solutions. Hi, on the next few slides, I'd like to solve a problem, and in this particular problem, the wave function will depend on the angle.
Terrific!
A hydrogen atom electron is in the n equals 2, L equals 1, ml equals plus 1 state. Calculate the probability that the electron would be found A, within 30 degrees of the xy plane regardless of the radius, between r equals 2a naught and r equals 6a naught, irrespective of the angle, and a combination of both a and b, which is within 30 degrees of the xy plane and between r equals 2a naught and r equals 6a naught. A naught represents the Bohr radius and is approximately 0.529 times 10 to the negative 10th meters. The wave function, we know n equals 2, L equals 1, ml equals plus 1, so the wave function is psi 211. Even if you were taking a class in quantum mechanics, you wouldn't go through and solve for this wave function every time. You solve for it once, and then you go and you take the solutions off of the table. And so here's the solution to the wave function. Now that we have this, let's go and solve problem A. Part A, we want to calculate the probability that the particle is within 30 degrees of the xy plane, so it's between here, and this would actually be for all directions. There'd be a circular region. We know that the radial probability distribution is the integral from theta 1 to theta 2, in this case of y11 squared times 2 pi sine theta d theta. We know y11, and y11 squared is given by 3 over 8 pi sine squared of theta. We'll then take this and plug it in, and we have to perform this integral. You can perform the integral any way you want to. When you do perform the integral, you get 0.68, or a 68% chance that you're going to find the particle within this region all the way around the circle. And then part B asks, what is the probability that we'll find the particle between 2a naught, which we say this is the inner radius, and 6a naught, which is the outer radius? For this case, we need to use the radial probability distribution. So we take the integral from 2a naught, which is r1, to 6a naught, which is r2, times r21 squared. Because we know we're dealing with a state r21, you have to multiply by r squared dr. We know the formula for r21 is here. We square it, we multiply by r squared, and this tells us that there's a 66.2% chance that we'll find the particle within this annulus of this ring. And finally, for part C, the probability if both the radial and angular ranges are restricted is just the product of the two fractions. So the probability is 0.688 times 0.662, and that tells us there's a 45.5% chance.
In this presentation, we set up the Schrodinger equation in spherical coordinates, discussed the boundary conditions, and presented the solutions without solving the partial differential equations. Visualizing these solutions can be challenging.
Unfortunately, I've run out of time in this video to discuss these wave functions in detail. That's going to be the focus on part 2 of the hydrogen atom in the beginning problem playlist. On the screen, what you see is n equals 7, L equals 3, m equals 2. You can choose the N, L, and M values here. There's not actually a cut within the wave function. The wave function really looks like that, but you can cut into it and see what's happening on the inside. And as you notice, for this wave function, you'll never find the electron here in the location of pi over 2. There will be a large probability to find the electron along this angle, but not at every single R position. For example, at this R location, you won't find the electron. At this R location, you won't find the electron again. Here, we have L equal to 6 and M is equal to 2. Now watch what happens as we increase ML. So we increase ML, the function is going to get more and more spread out perpendicular to the z-axis. So here you'd be able to find the electron in this ring and this ring, but there'd be no probability to find the electron up here or down here. And if you increase to where there's 90% probability, you can see what the distribution would look like. So on the next presentation, part 2 of the hydrogen atom, we're going to discuss these solutions, and that's going to be the focus of that presentation. AcePhysics.org. Math and Physics Tutoring with Dr. H. AcePhysics.org. Math and Physics Tutoring with Dr. Hudis.